When we use our distance and midpoint formula, we're going to use the exact same format as we did in 2 dimensions, but it's going to be expanded to 3 dimensions with a z term. So you know the distance formula in 2 dimensions was the square root of x2 minus x1 squared plus y2 minus y1 squared. Same exact formula is going to apply in 3 dimensions, except for we're going to add a z piece. So the distance formula in 3 dimensions, we originally had this, x2 minus x1 quantity squared plus y2 minus y1 quantity squared. That was 2 dimensions. Moving to 3 dimensions, we're just going to add a z2 minus z1 quantity squared. And that's going to represent my distance formula in 3 dimensions. So if I want to find the distance between -1, -3, -2, and 5, -1, 2 in 3 dimensions, we're going to do x2 minus x1 plus y2 minus y1 plus z2 minus z1 and square each of those terms. So in the first one, x2 minus x1, so 5 minus a -1 is 5 plus 1 quantity squared, plus -1 minus a -3, which is going to be -1 plus 3 squared. And then finally with the z's, 2 minus a -2, which is really 2 plus 2. So my distance in 3 dimensions is 6 squared plus 4 squared. No. -1 plus 2. I'm getting ahead of myself there. That's 2 squared plus 4 squared, which then gives me the square root of 56, 36 plus 16 plus 4. And the square root of 56 is 2 square root of 14. Your midpoint formula can also be applied to 3 dimensions. With the midpoint, you originally had x1 plus x2 divided by 2, comma y1 plus y2 divided by 2. You can probably guess what this is going to be in 3 dimensions. If you said z1 plus z2 over 2, you would be correct in adding that. So z1 plus z2 over 2 is going to give me my ordered pair, which is actually an ordered triplet in 3 dimensions, since we've got 3 points. So finding the midpoint between these 2 values, we are going to take our x values, add them together, divide by 2. Take our y values, add them together, and divide by 2. And take our z values, add them together, and divide by 2. Which will give me my midpoint. The last example here is I want to know what type of triangle do I get from these 3 points in space. And for this, we are going to use our relationships that we know about an isosceles triangle, a right triangle, or neither. So the relationship that we are going to use is that if we've got a right triangle, it is going to have a relationship that we know from our 30, 60, 90, 45, 45, 90 degree triangles. Or if we really need to, we could do some tangent inverses of opposite over adjacent to see what we come up with for our values. If we have an isosceles triangle, that means that we are going to have 2 angles with 2 sides that are the same length. If we have neither, that means we're going to have 3 different sides with 3 different lengths. So here I'm just going to draw these points in space. I really don't care if I have them oriented right. I just want to have them listed. And it's not going to be in 3 dimensions since I didn't draw this in a 3-dimensional space. But point A I know is 4, -1, and 2. Point B is 8, 1, and 2. And point C is 2, 3, and 2. So let's go about and we want to find the lengths of the sides of these triangles. And then we can see what types of relationships we have and do we have an isosceles right or neither triangle. So in order to figure out the lengths of each of the sides, I'm going to use the distance formula. I'm going to find the length of AB, I'll find the length of AC, and I'll find the length of BC. And for that, we'll use our distance formulas. So we'll start with AB. We'll do 8 minus 4, which will be 4, and we'll square that. We'll do 1 minus a negative 1, which is 2, and we'll square that. And then 2 minus 2, which is 0, and we'll square that, which is going to give me square root of 20. Or that same thing as 2 square root of 5. We'll do the same thing with AC. So where's my AC? AC is down here. And I'll look at 2 minus a 4. That's going to be negative 2 squared. 3 minus a negative 1. That's 4 squared. And then 2 minus a 2, which is 0 squared. Negative 2 squared is going to be 4. 4 squared is 16. So once again, I get the square root of 20, which is 2 square root of 5. So here we've got a square root of 20, or 2 square root of 5. And then finally, we've got BC. So we've got here 2 minus 8, which is negative 6 squared. 3 minus 1, which will be a 2 squared. And then 2 minus 2, which is 0 squared, which is square root of 40, which is 2 square root of 10. So as we look at this, we want to look at the relationships of our different sides. And we actually have two relationships here that we know. We can see that we have the exact same side lengths right here, square root of 20 and square root of 20, which then means angles B and angle C have to be identical. So that gives me an isosceles triangle. But I also have another relationship, and it's the fact that both of these are the same, and then this guy right here is times the square root of 2. And the relationship that you have with that is that if you've got two sides that are identical, and then the other side is square root of 2 times those legs, that's a right triangle. Specifically a 45-45-90 triangle, where these two legs are the same and the hypotenuse is square root of 2 times the legs. So if this picture were drawn accurately, it would actually be a right angle. Right here at A, it would be a 90-degree angle. Both of these legs being the same, and then this side here is square root of 2 times the legs, which means I've got the right triangle formula right there.